Okay, let's jump right in with a fascinating paper today. It's called MemRL, Self-Evolving Agents via Runtime Reinforcement Learning on Episodic Memory.
It's a dense title, but the problem it's tackling is really fundamental for LLM agents. It's the Stability-Plasticity Dilemma.
Absolutely. The issue is when you want to teach an agent something new, you're stuck between a rock and a hard place. You can fine-tune it.
Which is super expensive and risks what we call catastrophic forgetting.
Or you can use standard retrieval augmented generation.
And the problem with RAG is that it's passive. It just pulls in stuff that's semantically similar, which often means it's retrieving useless noise that just distracts the agent.
So the big idea with MemRL is to let agents self-evolve, but, and this is the key, without updating the core LLM weights at all. They totally decouple the stable, frozen LLM backbone
from a plastic, constantly evolving episodic memory.
And the mechanism behind this is the real magic. They use non-parametric reinforcement learning to actually learn the Q value of a memory.
Exactly. It's no longer about, does this look similar? It's about, was this actually useful in the past? It gives the agent a critic.
And the results speak for themselves. The paper shows MemRL consistently crushing baselines like RAG and MEMP across a whole range of benchmarks. It's solid proof that this utility-driven approach is the way to go.
You know, what I find really cool is how much they draw from human cognition. They talk about this idea of constructive episodic simulation.
Which is basically our ability to solve new problems by pulling up old experiences and stitching them together, right?
Exactly. And we do that without having to, rewire our entire brain every time we learn a new recipe or something. Our core reasoning stays stable.
That's a perfect analogy for the problem with fine-tuning. It's like trying to perform brain surgery every time you want to teach the agent a new API. You might teach it that, but then it completely forgets how to do something else.
And RAG was supposed to fix this. But its fatal flaw is that reliance on just cosine similarity. It's a very shallow understanding of relevance. It can't tell the difference between a high-value strategy and something that just uses similar keywords but is structurally completely wrong.
So the mission here, what MemRL sets out to do, is achieve what they call runtime continuous learning. The agent gets better and better after it's been deployed in the real world.
All while keeping that backbone model frozen solid? That's how you solve the dilemma. All the plasticity, all the learning gets pushed into the memory system.
Let's dig into that architecture, because this decoupling isn't just a concept, it's really baked into the design. They have the frozen LLM with its weights locked.
For stable reasoning, yeah. And then you have the evolving memory, which is where all the action, all the learning happens.
And that memory is very specifically structured. It's not just a text file of past successes. They use this core data structure, the intent experience utility triplet.
Right. So you have serialized the intent embedding, which is just a vector for the task description. Then the experience, which is the raw log of a successful solution.
But that third piece, QAller, the learned utility, that's the innovation, isn't it?
That is everything. It's the Q value. It's an estimate of the expected future reward you'll get from using that specific experience. It's the critic in their RL setup.
And this is where the whole framing shifts. They formalize this as a memory-based Markov decision process, an MMDP.
Which is a fancy way of saying that retrieving a memory isn't just fetching data anymore.
It's an action.
It is an active decision. The agent is deciding, should I use this memory or should I try something else? You're not optimizing the LLM anymore. You're optimizing the policy of how the agent uses its own memory. It's a profound shift.
Okay, so if retrieval is an action, you need a smart way to decide. That brings us to their two-phase retrieval mechanism. Why two phases?
It's all about filtering out that semantic noise we talked about. You can't just look at the utility score for every memory you've ever stored.
It would be too slow.
And you'd get weird results. So phase A is a similarity-based recall. It's a coarse filter. Given a new task, it just pulls a small candidate pool of memories that are at least semantically in the right ballpark.
And if it finds nothing, the LLM just goes it alone, pure exploration.
Right. But then comes phase B, the value-aware selection. This is where the RL critic steps in. From that small pool of candidates, it picks the final memory to use by maximizing a composite score.
A score that's a mix of similarity and utility.
Exactly. It's balancing how relevant is this with how well did this work in the past.
And they have that Lambda parameter that's like a dial between the two. If Lambda is high, the agent is all about exploitation.
I only trust what's proven to work, even if it's not a perfect match.
And if Lambda is low, it's back to just being standard arg, all about similarity, all exploration.
Finding that balance is key. And the actual learning, the part that makes it self-evolving, is the runtime utility update.
So after the agent tries something, it gets feedback from the environment, a reward R.
Maybe a task succeeded, maybe it failed. That reward is then used to update the Q value of the memory it just used. They use a simple Monte Carlo rule.
So it's just nudging that Q value to be closer to the real reward it just saw.
That's it. It's a simple, elegant temporal difference update. The agent is constantly correcting its own expectations about its memories, all without touching the LLM's weights.
And then any new successful solutions get summarized and written back into memory as a new triplet, so the knowledge base is always growing.
Now, for anyone thinking about using this in a real-world system, stability is everything. You can't have an agent whose performance is all over the place.
And they address this head-on with some pretty solid theoretical guarantees. Theorem 1 basically proves that the Q value estimates will converge to the true average reward.
Right, and it converges exponentially fast. But what's really important for stability is that they prove the variance stays bounded.
Why do we care so much about bounded variance?
Because if the variance could grow infinitely, your agent would become completely erratic. It would wildly trust a memory 1 minute and then completely ignore it the next, based on noisy feedback. Yeah. Bounding the variance means the utility scores are stable and reliable.
Okay, that makes sense. And then they frame the whole thing as a generalized expectation maximization process, a GEM process?
Yeah, this is a bit in the weeds, but it's the mathematical proof of global stability. It shows that the whole system is constantly improving. It alternates between an E step, which is policy improvement.
That's the value-aware selection in phase B.
Correct. And an M step, which is the value update, the Q learning part. By showing that this cycle always improves the overall objective, they can guarantee the system converges to a stable point.
Which is the mathematical way of saying it won't suffer from catastrophic forgetting.
Exactly. The updates are anchored to a stable policy over the memory, so the core model is protected.
So let's talk results. They tested this across 4 pretty different domains.
Yeah, code generation, embodied navigation in ALF world, OS interaction, and complex reasoning in HLE, a really good stress test.
And the numbers, especially in the runtime learning tables, are pretty clear. MemRL consistently comes out on top.
The cumulative success rate, the CSR, is a great metric here. It shows the agent's performance over its whole lifetime, not just a final snapshot. Yeah. And MemRL's CSR curves are always climbing higher and faster.
The ALF world result really jumped out at me. That's a complex, multi-step navigation environment, and MemRL got a last epoch accuracy of over 0.5.
Which was a relative improvement of something like 56% over MEMP, the next best baseline.
That's a massive gap.
It really is. And it tells you that in these complex procedural tasks where you have to string together a long sequence of correct actions, having that utility critic is a game changer. Simple similarity just doesn't cut it.
And they showed this generalizes too, right? On held-at tasks, MemRL still performed better.
Yeah, in ALF world transfer, it still had a clear margin over MEMP. This proves that the Q values it's learning are actually capturing generalizable, high-utility strategies, not just memorizing specific solutions.
The ablation studies really get into the nuts and bolts of why it works so well.
They showed that the RL component is absolutely critical. Without it, the learning curve is noisy and unstable. The critic is what smooths everything out.
And they tested that Lambda parameter, the governor, and they found, unsurprisingly, that a balance of 0.5 was best.
Because if you go pure RL with Lambda equals 1, you run into this problem they call context detachment.
Meaning what, exactly?
It means the agent starts retrieving memories that have a super high Q value, but are completely irrelevant to the current task. Like, it knows a particular Python debugging trick worked great in the past, so it retrieves that memory even when you've asked it to write SQL.
Oh, okay. So similarity has to act as a gate, as an anchor to reality. And then utility acts as the strategic filter on top of that.
Precisely. And one other interesting tidbit from the ablations. For the really hard reasoning tasks in HLE, a smaller, more compact retrieval setting actually worked better.
Quality over quantity.
Yep. It suggests that for complex reasoning, minimizing noise is far more important than just having a huge volume of memories to draw from.
So if we dig a bit deeper into the implications, there's this idea of MemRL as a trajectory verifier. The performance gain was way bigger in multi-step tasks like ALF world than in single-turn tasks.
By almost an order of magnitude, yeah. A 24 percentage point gain versus just 2.5.
And the reason is that by propagating that final reward all the way back, the agent isn't just learning to pick a good first step. It's learning to pick a memory that leads to a complete, structurally sound solution.
It's filtering out things that look good at the start, but are guaranteed to fail 3 steps down the line. That's a much more sophisticated form of planning.
And they showed the critic is actually reliable. There was a strong positive correlation, Pearson R of 0.86, between the Q values and the actual success rates.
So when the critic is confident, you can be confident. High Q really does mean high success.
But this is my favorite part of the paper. This is the really counterintuitive finding. Even in the highest Q value bins where the critic was most confident, there was still a small fraction of memories, about 12%, that were from failed trajectories.
Wait, really? So it's not just valuing success. Why would it hold on to failures?
Because they weren't just random failures. They were what the authors call transferable near misses.
Okay, unpack that for me. A transferable near miss.
Think of a trajectory that failed because of one tiny specific error. Maybe the agent misinterpreted an empty output from a command. The memory itself contains not just the failure, but a reflection, a corrective heuristic.
So the reflection provides a general rule, like if a command returns an empty string, it means X. And that rule is super valuable.
Exactly. The critic isn't just valuing binary success, it's valuing reusable guidance. It's learning the wisdom from the mistake, and it prioritizes that transferable knowledge. That is profound. It's learning why things fail.
Yeah. That completely reframes how you should think about an agent's experience. It's not just about collecting wins.
Not at all. And speaking of versatility, they saw this weird result on the HLE benchmark, the HLE anomaly. The tasks in that data set are all very different from each other, very low similarity.
So you'd expect generalization to be poor.
Right, but the agent still showed a huge runtime gain. They concluded it wasn't generalization, but what they call runtime memorization. It was just getting so good at memorizing specific, difficult solutions through repeated exposure.
So it can generalize when tasks are similar, like in ALF world, but it can also just brute force memorize when tasks are diverse and difficult. It's incredibly robust.
It is. And it reinforces their stability claims. They showed MemRL had a lower forgetting rate than Mem, and they attribute that directly to the normalization and the similarity gate keeping the utility estimates from flying off the rails.
So if you zoom out, what's the big takeaway here for building the next generation of agents?
For me, it's that MEMR really delivers on that promise of continuous learning by decoupling the model and the memory and then running RL on that memory.
And it fundamentally changes what memory even means for an agent. We're moving away from just passive semantic retrieval to active value-based decision-making.
The fact that the Q values can capture the strategic value of a near miss, of a mistake, that just opens up a whole new way for agents to learn.
It really does.
Yeah.
Instead of just trying to build a perfect memory of successes, maybe the next frontier is teaching agents how to explicitly learn to value their mistakes in a way that helps them generalize faster.
To accelerate the acquisition of wisdom, not just data.
Exactly. And, a final thought. They achieved all of this with a pretty simple Monte Carlo update rule. What happens when you start applying more sophisticated model-free RL algorithms to this decoupled memory space? The potential for even faster, more robust learning seems absolutely massive. That feels like a huge area for future work.